Okay, so today we're going to continue talking about CPU scheduling algorithms. And we will have some practical examples and different type of tracing these CPU scheduling algorithms. We have seen previously the Gantt chart, which is one way of tracing CPU scheduling algorithms. Today we're going to do that in a tabular format as well. One of the algorithms that we mentioned is the optimal algorithm for preemptive and non-preemptive scheduling. So for preemptive scheduling, we mentioned that the optimal algorithm is the shortest job first, if you remember, right? And for non-preemptive scheduling, the optimal algorithm is shortest job first, yeah? Okay, so shortest job first for non-preemptive, and shortest remaining time first for preemptive scheduling. These are the optimal algorithms. And we also mentioned that we can't actually implement these algorithms. We can't have an exact implementation of them. However, we can have some kind of approximations, okay, for these algorithms. The reason why we cannot implement them is the lack of knowledge for how long a process will be executing. We can't guess that, right? So this is one estimation of the CPU burst times that can be helpful for an implementation of the shortest job first or shortest remaining time first algorithms. The idea is to base our expectation on the history of previous CPU burst times, okay? The rule is very simple, okay? You can say that the expectation of the next CPU burst time equals to the previous expectation of the CPU burst time plus the actual time of the previous process. The actual time of the previous process. So if I have a process Bx currently executing, initially, at the very beginning, I should have a default CPU burst time for it, right? Because it's our first process, let's assume, okay? Let's say that P0, our first process to execute, okay? So we're going to have an assumption saying that this P0 okay, P0, it might need, what? Say 5 milliseconds. So this is a guess, okay? This is our own guess, right? Initial guess. Then when B0 actually ran and finished, we found that, okay, we found that the actual time of B0, this was the estimation of B0, right? We found that the actual time of B0 was not 5. It was what? 10, for example. So we had wrong expectation for the very first one, okay? Now, we can improve our expectation for the next process because we have a history now, right? We have a history. So we can say the expectation of P1, which is in this case the next process, okay, equals to, okay, we won't say that it is equals to the actual time of the previous process, okay, but we can say it is equal to the previous expectation plus the actual time, and maybe we take the average of that. The average of that. That's fair enough. So when I say I take the average of that, means I have given the history of expectation the same weight as of that for the actual time. When I say, for example, E of P1 equals to E of P0 plus A of P0 divided by 2, I'm taking the average of the two, right? Which is equivalent, as I'm saying that I'm giving 50% weight for the first one, which means 0.5 multiplied by EP0 plus 0.5 multiplied by what? A of P0, right? So in this case, I'm having like same weight for the history as of that for the actual time taken by previous process. Okay? And from there, I can get an expectation. So I can say it is actually 10 plus 5 divided by 2, which is 7.5, right? So now look at the expectation. At the very first, our expectation was 5, while the actual was 10. So the difference is 5, right? And then the next guess, we moved halfway, okay? Because now the expectation is 7.5, right? So here I'm giving the same weight. So I can say this is a weight, and here is what? Another weight, right? So let us call this weight alpha. Then this should be what? 1 minus alpha, right? So the summation of the weights, of course, that you give in any equation, okay, of this type should be equal to 1, right? So this is what we're doing in here. But I can give alpha something else. I can give alpha 0.3, and by that, I will give 1 minus alpha 0.7. Means I'm giving more weight to the actual CPU burst time, right, than that of the expected one. Let's just proceed with the same weight. Then I will be having what? I'll be having 5 plus 10 divided by 2, and that's equals to what? 0.75, right? Sorry, 7.5 milliseconds, okay? This is our expectation. And now when we run P1, we found actually the A of P1, okay, was what? Was not 7.5, it was again 10. Again 10. So we have wrong expectation. However, the error is much less, 50% jump less. So if I keep this having the same weight of alpha, each time I will go nearer to the actual value by 50%, right? So I'll be much nearer, okay, to that. So now I can say that E of P2 equals to E of P1 plus the actual of P1. And if, again, I'm using the same, that will be what? That will be E of P1, 7.5, plus the actual is 10, and divided by 2. So that's 17.5. And 17.5 is very near to what? To 10. So I'm reaching what? I'm reaching almost, huh? I'm reaching nearer to what? 10, which is the actual, right? So in systems, okay, where these processes, okay, they exhibit very much same pattern for a while, and then they jump out of a sudden to either up or down by increasing or decreasing CPU burst times, I can maintain, okay, I can maintain that my expectation is almost the same as the actual. I will have maybe wrong expectation for the very first 2, 3, okay, quite far, and then after that, very fast jumps to what? To the actual value. Usually systems, okay, if this is time, okay, if this is time, and this is the CPU burst time, okay, usually like you find the processes like this one, for example, 10, these processes, okay, they stay what? They stay almost the same with time, okay. Here I have different processes, okay. I might have here B0, P1, okay, executing at this time. Here maybe I have P2, okay, and so on until P what? K. Most of the time they are around that. Around what? Around 10, okay. So my guess might be only different here. At the very beginning, it was 5 here, right? And then it jumped what? Halfway through. And then it's very much near here. This is the actual, right? This is what? The actual, A. And this is what? The expectation. The expectation, it goes very much the same as of that, okay, for the burst times, okay? This continues until BK, and BK is quite large. And then out of a sudden, we might have maybe a drop, okay? A drop, which means, like, out of a sudden, we have PK plus 1 has the actual value of what? Of maybe 3, okay? And then I have, again, my expectation will be between 3 and 10. So 7.5 divided by what? 13 divided by 2, that's 6.5, right? So I'll be somewhere here, my expectation. Okay, 16 is 6.5. Okay, because 10 and 3. So, okay, it's wrong, and then it might maintain here, the actual maintain here for quite some time until P what? PM, okay? So here again, I'll be moving fast to this, okay? So only for these periods, okay, for very short periods, okay, I have what? Here is longer, okay, the time. So here I only have kind of problem, which is wrong expectation, and here, but the rest is okay. So this kind of estimation is fine, right? Is fine. I mean, but however, it needs what? Collection of information, history, and evaluating this kind of equation and so on. So let's follow that in a simple example. Yep. No, this is time that you're looking at the system. The time I'm looking at what? The system. This is CPU burst time. Of course, during this time, okay, I have the execution of different type of processes. Okay, different type of processes. Okay. So now if we look at the one simple example, okay, you can say that we executed a number of processes and we found that their actual times were these. Okay? Were these. However, when we did the estimation for the CPU burst time, we started by saying the very first one, okay, the very first process will take 5 milliseconds. 5 milliseconds. So the first process, we expected it to take 5 milliseconds. However, it took what? 10. Which means the next guess will be the previous one, expectation, plus 1 minus alpha multiplied by what? The actual one. So we have 0.5 multiplied by 5 plus 0.5 multiplied by 10, and that's 7.5. Okay? So this is the expectation for the next one. And then if we go for the other one, okay, it was 10 again, right? And in this case, we say that the expectation of E3 equals to 0.5 multiplied by the expectation of E2 plus 0.5 multiplied by the actual of E2. So this is, the expectation of E2 was 7.5 and the actual was 10, so we are very near to 10. That's 8.75, okay? And then we execute the other one, which is E4. E4, look at it, 1, right? Usually, we stay longer there with processes that have similar CPU burst times. But to show you in this example that we might have what? Dramatical, okay, change of the actual CPU burst times. Here, the actual CPU burst time was 1. So when we did the expectation, we based it in the history of E3. Okay, in fact, it's not based on the history of E3. It is based on the history of 3, 2, and 1. Because the history of 3 is based on 2, and 2 based on 1, and so on. Okay, so this is a cumulative, okay, history. So we say that E4 equals to 0.5 multiplied by the expectation of E3 plus 0.5 multiplied by the actual of E3. Okay? Here, so this is E3, right? This is E3. So we found that it's what? 9.38, which is very near to what? To 10. There is one more 10 here, right? And now, after that, we have 1. So 9.38 is almost 10. We almost reach perfect what? Expectation. However, when it comes to the expectation of the other one, which we've seen that its actual value is 1, we find that it's 0.5 by E4, which is 9.38, plus 0.5 multiplied by the actual of E4, which is what? 1. 1, right? We expected it to be something like this, okay, if it was E4 10, right? However, if the A4 was 10, right? And then it was what here? The E5, when we calculated the expectation of E5, we calculated based on E4, right? So E4, the expectation of it was near to 10. If the pattern continues like that, we're fine, okay? But it was not like that, okay? Then look about the expectation of the next one, which is E5, okay? Our expectation now is 5.19, because why? Because A4 is what? 1. So we also move fast, okay, halfway through so that we can reach the actual, which is 1. And then the next one of E6, you find that the expectation is what? 3.1. And then it's what? 2, very much near to what? 1. So if the button continues there at 1, we are safe, right? And usually that's the case. However, there are dramatical jumps, okay, either up or down, decreases or increases for these burst times. So this is how the estimation is done. That was a note on the estimation of CPU burst times that can be used for approximations of shortest job first and shortest remaining time first scheduling algorithms. Now, I also mentioned that there are other types of scheduling algorithms, including multi-level, okay, queues. So we have here more than one queue, right? And in this case, I have, as you know, I have different processes in the system. And usually these processes, they have what? Different priorities, right? So I could have ranges of these priorities, processes priorities. I could have ranges of them to be in different queues. Or I could have the same number of queues equal to the same number of priorities that I have in what? In the system. This is done usually by partitioning the buffer, okay, that holds what? The processes, okay, the run queue, which means the run queue is what? Priority queue, is what? Priority queue. Or I could have really, okay, physically different, okay, buffers, okay, different buffers, different queues, and so on. So in this case, the question is, okay, how many queues I need to have, okay, and which processes should be queued in which queues, okay? So in this example, I have like 5 different queues, and I decided to have system processes in the first queue, interactive processes in the second, and then interactive editing processes in the third, and then batch processes in the fourth, and lastly, student processes in the last queue, giving it the lowest priority. So in this case, I'm like preferring what? System processes. Because they are much more critical and they need to be executed first. Now the execution. I have one CPU assumption, okay? Which one of these queues I should serve? The highest priority, okay? And then the one with least highest, and so on, right? But for how long I should serve a particular queue? Assume that I have started serving here. Should I keep serving this queue until all processes finished? And only then move to the next one? This is one way, right? But here I'm using what? Strict priority, okay? Strict priority. You can only move to the next queue only if this is what? Empty, okay? Strict priority. Now, if this one, I served all the processes in it, or system processes, and then I move to the next queue, which has interactive processes. I also need to keep serving it until what? It's empty. But assume before it was empty, halfway through, assume that I have a process arriving here. What should I do? That's another question. Should I go back and start serving the system processes and preempt the process that I was serving here under interactive processes? Or should I say, no, I have to be fair, okay, I already given this the time it needs, now I should give the other queue, which is interactive processes, the same way, treat it the same way, and then move to the next one, and so. All of these are questions, and they have different answers, okay? Whatever answer that you give, still acceptable if it really suits you the best, okay? Based on the system and the kind of processes that you have. So we have multiple questions. So if I give you this figure and I ask you this question, think as a designer, okay, what kind of questions you need to answer to implement a CPU scheduling algorithm for a system, not given any other information about the system. So now you have to think of all possible ways of doing so, okay? How many queues? What should be held by these queues? which queue to start service, how should I service the queue, okay? And should I preempt back to higher priority queues or no, right? And if I am serving one particular queue, this is another question. Assume that I'm serving this queue now. How should I serve this queue? Should I serve it based on first come, first serve, or round robin, or any other scheduling policy? Which means also each queue has its own what? Scheduling policy, right? So all of these are questions. One might say, well, don't serve priority. Let us serve these queues, what? Round robin. What do you mean round robin? Well, I'll give certain amount of time to serve this, and then certain amount of time to serve this, and so on. If this amount of time is equal, means there is no point of having queues. One queue is enough. But if these times are different, okay, then I'm favoring the first queue by giving it more time to serve, okay? Say that I'm gonna serve this queue for 500 milliseconds, while this queue I'm gonna serve it for 300 milliseconds. This one for 50 milliseconds, and so on. So you're giving what? More time to serve certain queues than the others. This is another way. Or someone might say, okay, I'll be serving this queue, okay, until a particular threshold. What's your threshold? The condition, a condition. Say that I'm gonna serve this queue, okay, as long as the length of it, okay, is not more than, the length of it is not more than 10% of its capacity. 10% of its capacity. Which means if the queue is full, you're gonna serve 90% of what's in there. Until it's only the size of it is 10% of the capacity, then you can move to the next one. However, the next queues, you might say 30%, 40%, and so on. So all of these are questions that you might have. So different scheduling policies for each queue, and you need one general scheduling policy to go from one queue to another. One problem with this kind of scheduling that processes with lowest priority queue might starve for service. Okay? This is called starvation problem. Starvation problem. And one way to deal with this kind of problem is by what? Increasing the priority of these processes. Increasing the priority of these processes. This is one way. Okay? On the other hand, we might have what we call multi-level queues, but with what? With feedback. With feedback, it means that the process can migrate from one queue to another. Can migrate from one queue to another. Again, these queues, they might have what? Different scheduling policies, okay? So one way is to have like the very first queue to serve is a FIFO queue, and all of them FIFO queues until maybe I reach the very last few ones where I change to round robin, okay, policy of serving these processes. How does it work? A process getting service here from the first queue, if it's finished, it's fine, I'll take the other process and so, okay? If it's not finished, say PX is here, not finished, then it has to queue back, right? But in the queue with lower priority. In a queue with what? Lower priority, okay? And so on. It keeps going that way, migrating from one queue to another. So these are some of the questions I already mentioned it there on the slide. In case you've forgotten, okay, the discussion, you can refer back to this, and you can add more questions as well based on the discussion we had. Another example of these multi-level feedback queues is this, like having three queues, Q0, 1, and 2. I could choose for the first one to have the round robin policy, okay, where we have 8 milliseconds quantum time. Usually, if the highest priorities, okay, of these queues, the ones to be served, if they are round robin, they have less quantum time. And then the next one, they have more quantum time. Because a process, if it could not manage within 8 milliseconds, okay, then a conclusion, it needs much more than 8 milliseconds, okay? But how much more? I don't want the same problem to be repeated for this process to take another 8 milliseconds. So I'll increase the possibilities of this process finishing when it moves to what? To the next queue. So here 8 milliseconds, okay, the process is not finished, which means it needs more. If the next queue here is 8 milliseconds, well, there is no point, right, of having these two queues. So I'm going to say quantum time equals to 16. Hopefully, next time this process gets the service here, it will complete, okay? It will get the service until it is completed, okay? And the last one would have it what? First come, first serve. For sure, you're going to complete there. Unless you've been waiting for I/O or things like that, you will be requeuing in that queue. But is that all about CPU scheduling? It's not. There's a little more about CPU scheduling. It's actually a field that has lots of algorithms, okay, and lots of applications as well. One important problem with scheduling when we have multiple processors. Multiple processors. So far we have one processor, okay? Or in general, scheduling one service center. One service center. So here, if I have multiple processors, then I need to ask other type of questions as well. Other type questions. One of the questions might be, okay, are these processors with the same performance? Are they homogeneous or heterogeneous? Are they similar or not? Okay, that's one of the questions. Another one, I need to distribute the load among these processors. I don't want to have like a few of them continuously working while others are not working. Most of the time they are idle. I want to make them busy all, okay, with the same percentage if possible, okay? And the third one, how independent these processes from each other? Is there like one processor who has control on the others in terms of scheduling or no? I mean, is there one processor that is dedicated to do the scheduling or no, right? So if we might have one processor, okay, that processor has the scheduler, okay, and basically what? Do whatever related to the scheduler in terms of tasks to find out which processes to queue at which processors. Which processes to queue at which processors, okay? Having that each processor has its own run queue, which is the ready queue. Each processor has its own run queue. So every processor has its queue. However, how processes arrive to this queue? Okay? Who will take the decisions and do the calculations to find out which process goes to which processor? Okay? All of these are questions that we need to ask. Additional questions might be related to processor affinity. Affinity, which is basically, if one process had been running on processor X, now that process might take turns, right? It might be rescheduled, right? Now, the next time it takes the turn, will it take it at the same processor or on another processor? That's another question I have to answer. What's so important about this question? I mean, it doesn't matter this process whether it's running on the same processor the next round or on a different processor. Does it matter? Does it matter? It matters. Why? You heard of the cache? Right? So basically, this process, when it had been executing on a processor, okay, it had been cached, right? So the next time it is to execute, okay, it's already in the cache there, right? So the re-execution of it, restarting this process is much faster than it is migrating to another set of execution, which is another processor, right? So this is called processor affinity, okay? But if I am to do that, you know, then that might contradict with what we call load balancing or load sharing, okay? Load sharing, because assume that I have assigned 5 processes to a particular processor, okay? And these so I have assigned, I have here like a processor with a particular queue, another processor with another queue, and so And I have given here 1, 2, 3, 4. Okay? Here I have given only 3. Okay? And here maybe 1, 2, 3, 4, 5. Okay? 6. Okay? If I say that, okay, the process here, Px, when it takes its time, it's rescheduled on the same queue, then if the processes in this queue tend to be, okay, tend to need long CPU burst times, okay, if the processes in this queue for this processor tend to need long CPU burst times, then it will take them much longer than serving the other queues. So at one point of time, okay, after some time, okay, what would I have? I would have this is empty, okay, while this one is still serving these 3 processes, and this one is what? Empty. Correct? I did that for affinity, okay? Because I want things to be faster. But I end up something like this. So these 2 things, they contradict, okay? Affinity and load balancing. They might contradict based on the nature of the processes that we are executing. Other things are related to real-time scheduling, okay? So other type of scheduling algorithms are real-time scheduling algorithms. And for real-time systems, we have certain constraints. We mentioned before that we have 2 types of real-time systems, or 2 categories of them, hard and soft. Hard and soft. Usually, the process is real-time if it is supposed to get its response within a deadline. Within a deadline. Okay? So there is a lifetime for this process to get the response. Okay? So if the response is less, response time is less than the deadline, it's excellent. Right? So this is what we want to achieve when we design real-time scheduling algorithms. We want the response time to be less or equal to the deadline, okay, for that process. Okay? So each process has a deadline, lifetime, to get the response. We want response time to be less or equal to the what? To the deadline. Hard real-time systems, they add a little bit more constraint, saying that we want the deadline, okay, the response, okay, we want them to be almost the same. Almost the same, which means processes executing, okay, at certain times, right? Exactly, almost exactly at certain what? Times, okay? So from there we define actually the performance measure that is called latency, okay? Latency, which is equivalent in this case to response time, okay? How long it took, okay, for the processor to respond to the process. Response time, right? And we introduce another one called jitter. Jitter basically is the variation of latencies. The variation of what? Latencies. Okay? And we need this to be almost zero. Almost zero for hard real-time systems. For hard real-time systems. Okay? Which means if I have a process or I have 2 processes and their deadline is 10. Okay? 10. They correspond to a particular hard real-time system. If I found that the response time is 8 and for the first process, and the second process, the response time is 8 again, then the jitter is what? 0, because it's the variation between response times, right? However, if I found that The response time for the first process is 10, which is still acceptable, right, in real-time systems. And the response time for the second process is 6. Then the jitter is what? 4. And that's a big problem in hard real-time systems. This is actually the main measure in hard real-time systems, okay, the jitter. We do want variations. We actually expect these events, okay, to happen, okay, and the time between them happening, okay, the differences in times is what? Is fixed, okay, is fixed. So variation of response times. Another type of scheduling is called thread scheduling, okay, where when we talk about threads, we will elaborate more about it. Basically, a thread is a lightweight process that lives within a process. It's a lightweight process that lives within a process. In fact, it is what? A simpler representation of a process. Okay, and when it is executed, in general, we say it's executed by what? Encapsulating it in a lightweight process. And who will decide on scheduling these lightweight processes? The kernel itself. Now I promise to go through a tabular way of tracing the CPU scheduling algorithms. So backup 1, I have here round robin. I have preemptive shortest first, and I have preemptive priority. I think we did not do anything about priority, right? So we do preemptive priority scheduling, okay? And we're going to trace it this way. Okay? The tracing format. This is very much like what we are intending to have for a simulation of CPU scheduling algorithms, okay? What you will see in here, the trace, okay, usually your program will not show it on the screen because that will cause lots of delays, right? You're displaying data on the screen. But what we can do, we can save this in a file. Okay, we can save it in a file, and later on we can look at this file and study it more. The idea like this, consider that you have the following processes. Okay, we have P1, P5. We have arrival times, we have burst times, and we have priorities for these processes. And we are asked to trace the execution of these processes in this tabular format, where we have one queue, one CPU. Okay? So we'll start by the arrival time, and I already given you the arrival time, okay, ordered. Okay? Now, the way to do is to have this kind of formats. I need to determine what's the event. I might have one of two events happening here, okay? Because my system is as simple as this. I have one queue and one CPU. This is the run queue, and sometimes I refer to it as the ready queue, and this is what? The CPU. And I have here what? Arrival, and I have departure. Okay? Arrival of processes, of course. At the very beginning, the queue is empty. Now, the very first event to happen here is an arrival. So I have an arrival, okay? And the time for it is what? 2. And this arrival is what? P1. P1. Now, P1, when it arrives, the queue is empty. So will it queue? Will it queue? It's empty, the queue. So it will get into service immediately, right? So I have P1 getting into service, and it needs how long? 7 burst times. What's the priority? 5. Priority is 5, right? So I'm expecting this to finish when? At 9, right? It started at 2. It needs 7. It will finish at 9. So, of course, all the events here, I will have like a departure event, okay, at 9. And who's departing? P1, okay, P1. Or I can just simply write 1, okay. This is the departure list, okay. In the simulation, you will have the arrival and departure as one list. And that list is ordered by time. Okay? In fact, it's ordered by time and event type. Later, I will show you exactly how we can implement that. Okay, next. Is there an event happening before the time 9? Before the departure of this? Yes, there is. Actually, there are 2 events. Okay? So I'll have at 5 an arrival. And the arrival is P2, which needs what? P2, it needs 3 milliseconds. What's the priority? 1. 1 here, lower means higher priority. Okay? Here it's higher priority. The least, the number is the highest, the priority in this case. Okay? So it is higher priority than this. And what I'm doing here, I'm using preemptive. Look at it. Preemptive, which means I'll preempt this. Okay? Because the one arriving, higher priority. So P2 now will get into service, and it needs 3 milliseconds, and its priority is 1. Which means P1 was preempted. After how long? After 3 milliseconds. Which means how much left? 4 milliseconds. Okay, so this is P5. And it's in the queue. It's in the queue. Right? So now this event is not valid anymore for P1. Isn't it? Now, I had an arrival, okay, who got into service. Usually, whenever you start servicing a process, immediately you schedule its departure. Immediately, you schedule its departure. This is one important thing in simulation. Okay? So this one started at t equals to 5. It needs 3, expected to leave at t equals to 8. And that is P2. However, do I have anything happening before 8? Yes, I have. I have an arrival. Okay? So that's why if these 2 lists are merged, you'll just serve the first. You always take the first one because they are ordered based on time, right? Okay, now 7, I have an arrival, and the arrival is P3. P3 is priority 3, and the one executing is priority 1. So I cannot interrupt it. I cannot preempt it. However, P3 is of higher priority than the one currently in the queue. So P3 will what? Will queue in front of P1. So P3, and it needs how long? 10. And priority is 3. And the one here is P1, 4, and priority is 5. Now, at this point of time, P2 is left with how long? Look, elapsed how many seconds? Milliseconds? 2 milliseconds. Here it was 3, so now it's left with what? 1 millisecond. It is left with 1 millisecond. So now I have, again, an event which is departure event at 8. However, I have an arrival, the next arrival is at what? 15. Okay? So I will be now executing what? A departure. Right? So the departure, who's departing? Departing? P2. So now P2 is out. And what's the time? 8. I have a departure. If this one is out, then I immediately take another process. So always, this is again in simulation. When you do departure, check the queue. If it's not empty, take a process to execute. Okay? Keep that in mind. So now P3, okay, 10, 3, and the one in the queue is P1, 4, 5. Okay? Since I already took a process to execute, okay, then I'll schedule its departure. Its departure at what? 18, right? And this is P3, departing at 18. Okay? However, I have some other arrival at 17, which is at 15. That's before 18, right? So I have an arrival at 15, and the arrival is P4 that has priority of 2. Okay? Priority of 2 is even higher than the process under execution, which means it will start here. So this is P4, priority 2, and it needs how long? 2 milliseconds. Or 6? Okay, 6 milliseconds. Yes, 6 here. Okay. Now, this one was interrupted here, right? It was preempted. Okay? It preempted its priority 3, so it will be where? Here, in front. Priority 3. And how many milliseconds left? At 8, it needed And then I'm now after what? After how many? After 7. Okay, 7, right? 7, so it is left with 3. 3. 8 to 15 is 7 milliseconds. It was 10, now it becomes what? 3, okay? So now, after that, I'll still have, of course, P1 that needs 5 in here, okay? Now, since I already started the execution of this, I have to schedule its departure as well, right? So the departure of this is expected to be at 21, a departure of P4, okay? However, P4, okay, 21, but I have an arrival before that, which is P5 arriving at 19, okay? So I have an arrival, okay, at time equals to 19, and the arrival is B5, which is priority 4. Priority 4. So I will have P3. Huh? Ah, excellent. See, most of the mistakes of the students are simple. Simple mistakes, okay? But at the end of the grading, we won't know whether you just basically being quick or what, you don't understand, so please be careful when you do the tracing, okay? So what I have in here, I have B5 instead of B1, okay? B5 because it has higher priority, that is 4, okay? And it needs 2 milliseconds. This is 2 milliseconds, okay? So now I have here, the last one is B1 4. Look, B1 started first. It turned out to finish last, okay? So now, at this point, I have B4, that's priority 2, and it's left with 2, right? Because the time from here to here is what? 4, okay? Which means left with 2, okay? Now, do I have any other arrivals? If I don't have any arrival, of course, this we said was B2 was valid, right, and executed. However, this one at 18 was not valid, okay? And so now this one expecting it to depart at t equals to 21, right? So departure 21, and here what I have B4 departing. Okay, so now we'll take over P3, that needs a 3, okay, and I'll have P5, that needs 2, 4, okay. You cannot repeat these, okay, if the order is not changing here in the queue. Now I schedule this one, means it will be departing, that's P3, and it will depart at t equals to 24, because it needs 3 milliseconds, okay. And what I'm going to do, actually, I will execute the departure. So I schedule it and execute it because no more arrivals, right? So this is departing. So now departing, sorry, it had been done. Yes? Oh, sorry. So now okay, B5 with 2 needs priority of 4, that needs 2, right? And here I have P1, 4, to 5, okay? Okay, so this one will be departing at t equals to 26. So 26, I have a departure of P5, okay? And I'm going to do that, 26, departure P5, okay? And I have other departures before, okay? So now I have P1 getting into service, finally. This is empty, okay? And this will be departing at t equals to 30. I have a departure of what? P1. Yep. Yeah, here we just have the tick here that it had been departed. In fact, when you do the coding, you will be deleted this event. You will be deleting this event anyway, okay, when you do the coding. You will check, okay, the event, whether it's valid or not valid, okay, and whether to be executed or not to be executed. This is encoding, okay? Yeah, it took it, okay? Yeah. Okay, so now the last one, departing at 30. So I have a departure at 30, and basically this is P1. So I have them all. This is idle, this is empty. This is what we do, right? So now, most of the time, all of this work can be asked in one question, okay? Write the order of execution. So basically, you are asked to write this. But any mistake there, 0, okay? But usually, when we do this thing, okay, we want you to be, to understand the algorithm. And if you really understand things, then you can code it. Which means if you can code it, for sure you understand it. So that's why you'll be coding this, okay? We need to code this. Now, if you calculate the waiting time, we'll do that because we don't have much time left. You just calculate P1, okay, the waiting time for it, and the response time, okay, for P1. Waiting time and response time. Okay, let's see P1. P1 arrived at T equals to 2. You can even not to look at this one. Basically, P1 in service, and this is at the very beginning of the simulation, okay, arrived to and get in service 2, which means response is 0. Okay. Now the waiting time. The very first waiting time is 0. And then it appeared here in the queue at T equals to what? 5. And when it left the queue, at T equals to 26. So from 5 to 26, P1 was doing what? Waiting. Okay, so that's 21. Okay, the waiting time is what? 21. So you look at the process, when was it in the queue? Okay. For how long? When did it disappear? Okay, that's one waiting time. And then you look again if it appeared again or no. In this case, P1 did not appear again, and so. Okay, so please do the calculations for the rest of them. And this is, going through this example, maybe give us some kind of ideas how to code this. Yep. But you still need to, to see a code or maybe to craft the code together so that you'll be really able to simulate such CV scheduling algorithms. There are similar papers, okay, practice papers or sheets that you need to do.